need a rapid approach, we need to do 1 billion experiments at a time. 1 billion experiments at a time is kind of hard. And so it's a process called combinatorial chemistry. How many people have heard of combinatorial chemistry? Basically, it's a way of doing lots of different combinations at once and trying to basically find the one that meets the particular kind of requirement that you're looking for. Now, one way of doing this is actually through DNA engineering, which we're going to talk a little bit about. But so DNA is pretty inexpensive. Proteins is much more expensive. So instead of going through and making 1 billion different proteins and testing that, we're going to do this at the genetic level because doing genetic engineering is a lot easier. So when we first started thinking about this, we decided to use a bacteriophage, a kind of virus. Bacteriophage are viruses that only infect bacteria. They have single-stranded DNA. It's very simple. We have high school students in the lab always come in and can work with these particular kind of viruses. These are completely non-toxic to humans and are actually FDA approved and used in medical diagnostics. Bacteriophage are also sprayed on your lunch meat. Not our bacteriophages, but to reduce actually bad bacteria making you sick. So we can actually go in and take the single-stranded DNA, and through just using simple genetic engineering, we can actually cut and paste it and add a random DNA sequence to our virus. Now, this virus is a very simple structure. It has this DNA, and it actually is made out of a protein code. So by going in, this DNA codes for this protein. By going in and making genetic modifications in its DNA, it actually makes modifications in the protein on the surface of the virus. So yellow gene here, yellow protein. Now you can do this 1 billion times and get 1 billion viruses that are all genetically identical to each other, but they're going to differ just based on their tips, their chemical functionality. Now we're going to use that as a library. So when you have 1 billion different molecules, you call it a library. And we're going to take our 1 billion different viruses. In about a 1 microliter sample, you can put 1 billion viruses. So you can take them, and now you can force them to interact with any kind of materials you want them to interact with. This could be a semiconductor used in your computer chip. It could be magnetic materials. It could be materials for solar. And now what you ask these viruses to do is say, can any of these viruses learn to interact with this material that it's never had the opportunity to work with yet? Okay? Of those 1 billion possibilities, you'll have a couple of them that will find a chemical match for this surface, for this particular kind of material. All the ones, see this one's falling off, all the ones that didn't match get washed away. Anything that actually could bind to that surface, we keep that. Now we infect it into its bacterial host, and now the bacterial makes 1 million copies of this particular virus. We call it a clone. And so now we have this factory, this bacterial factory make millions of copies for us, and now we force them to interact with that same material again. It's kind of a Darwinian process, survival of the fittest. Of these 1 billion, which is the very, very best for interacting with my material of interest? And so my students can do that in about 2 weeks. They can find a winner for lots of different kinds of materials. Here's the current applications that we're looking at in my lab. Batteries is a big area that we work in, basically virus-based batteries. We work in an area called electrochromic devices. These are simple displays, a couple of color displays that could be used for things like smart cards for credit cards. We work in solar cells. We work in very high efficiency solar cells, and we work in very inexpensive spray-on solar cells. We work in catalysis in the area of water splitting. How do you take sunlight and water and turn it into hydrogen for fuel? We work in fuel cells also for energy applications. We work in fibers for incorporating batteries into textiles for soldiers' uniforms. We work in nanoelectronics, medical diagnostics for colon cancer and breast cancer detection, and we work in carbon capture and sequestration. This is a project where we're using another organism, yeast, not viruses, to capture CO2 from a coal plant and convert it into calcium carbonate for building supplies. It's all done through genetic engineering, training the organism to learn how to take CO2 and turn it into something useful. It can be done in the order of a couple of weeks. So these are the major topics. I've never been accused of being focused. So this is a genetic toolkit that you actually just go in and you make simple modifications. You can go in and do cut and paste and make modifications in this gene called gene 3, and that'll make modifications in this end of a virus here. You can go and make modifications in this gene called gene 8, and that expresses actually 2,700 copies of a protein on the code of a virus. So it's a virus as a genetic toolkit to grow materials. Now, another thing that's nice about this organism, this virus, is that it's actually 1 micron in length and about 6 nanometers in diameter. And every time it replicates itself, it's always exactly the same length. I tried to be a polymer chemist for a couple of weeks as a postdoc, and I wasn't very good at it. And one of the reasons is you go and you make these synthetic organic polymers, and they come in lots of different lengths, and then you actually have to go through and figure out how to size separate it and get them all out. And I didn't really have the patience for that. But in this case, biology likes to give you things in exact units. If you have a protein in your body and it's too short, has a mutation in it, it can lead to disease and all kinds of problems. So why not exploit this, something called monodispersity of biological organisms? And so this is, I'll tell you a couple of stories depending on what time I have. This is an idea of a student of mine, and as you guys are thinking about going to graduate school, it's always good to apply for your own fellowships, because when you go into graduate school with your own money, it gives you a lot more flexibility. So this is a really brilliant student of mine. His name's Asher, and he wanted to, came in with his own money. He wanted to see if he could use a virus to find very rare events in a semiconductor, and I'll tell you about using it for something more useful in a minute. And he's a really smart student, graduated #1 in his class at Berkeley. And I said, it sounds like a good idea, but I don't think it's going to work. So good luck. Give it a try, and we'll see how it works. And so here's this idea that when you grow 2 different materials where the atoms are spaced differently on top of each other, and you grow them right on top of each other, this will make sense to you from other ideas. There's a mismatch in the stacking of those atoms. And that mismatch in the stacking of the atoms actually leads to an atomic level defect, an atom that's in the wrong place, basically. And that can lead to all kinds of problems. This is one reason why LEDs are expensive. It's one reason why very high efficiency solar cells aren't more efficient than they are, because in order to get the broadest range of light collection out of solar cells, a lot of times you need to put a lot of different kinds of materials together. Okay, that can lead to problems. So his idea was take something that you knew had some defects in it, train a virus to bind this defect, not bind a perfect surface, bind the defect, not bind the perfect surface, back and forth. This is why I said, kind of good luck, give it 6 months and see what happens. And he was able to pull out 2 out of 1 billion sequences that could recognize atomic level defects in a semiconductor. And I'm like, oh yeah, I knew that would work. And so then he took a fluorescent tag and he added it to these materials. And so now he can actually go and, like when a wafer comes off the fab line, he can count the number of defects by just looking at the fluorescent signal. And that was kind of neat. And this is him, he got a good job and went on and it was kind of neat. But we started thinking about larger materials. What about airplane engine blocks? What about when you take an airplane material, it's a super alloy material, wings and engine blocks are, and when they go through fatigue damage and they get pushed back and forth, it leads to cracks. Well, the chemistry of a crack is slightly different than the chemistry of the surrounding. And just like an antibody can recognize some slight difference in something that's in your body, you can train viruses and yeast to find small cracks in airplane engine blocks. We're actually working with several large companies now in airplane engine blocks and in large-scale equipment for oil drilling to train organisms to find and sit on a defect and give off a signal. Okay, and so that's kind of where Asher's work ended up going. So from the very, very small scale to the very big scale. Well, that was actually really fun, but what we really wanted to do was train organisms to grow materials. And so this is a cartoon of what a virus would look like if it could grow 4 different little semiconductors, electronic materials, on its tip. And this is a transmission electron micrograph. It's a 1 micron length scale here of a virus that's actually grown 4 or 5 semiconductors on its head. This is a pretty high resolution image. This is a little bit higher resolution, and this is a little bit higher resolution over here. So this is actually, I think, around 800,000 times magnified. Can you guys see those stripes, dark light there? Those are atomic lattices in a crystal. And so these viruses have been trained to template a material, and then you give it a semiconductor precursor, just zinc and sulfide in solution, and it grows a semiconductor particle on its head. And so we thought that was really, really cool. We published it in a high-impact journal, but I don't think it's really changed the world technology. And then we started thinking about viruses themselves, how they're always the exact same length. And we started going through and engineering not the tips to grow materials, but the whole body to grow materials. Because, as a material scientist, this isn't a virus, this is a wire. And can we get it to actually grow electronic material for a wire? And so we could. This is actually a virus that's been engineered to grow silver nanowires here. They're all grown at room temperature. You pour in the silver, they grow the material for you, all done at room temperature. There's actually no reducing agent for those chemists in the group as well. But you can also give a virus multiple genes to grow multiple materials. This is a virus that we engineered to grow 2 different semiconductors side by side, zinc sulfide and cad sulfide. So once it has the right genetic information, all you have to do is give it the precursors, and it grows you this hybrid semiconductor material. Definitely very, very fun. So this is actually showing, this is a virus that's growing multiple kinds of materials. This is an an elemental map showing zinc and cadmium, showing you that it's actually growing these materials. You guys probably don't have an atomic force microscope here yet, is that right? You guys should get one. Basically, atomic force microscopy is a way of looking at structures and even DNA at very high resolution without having to look in a high-resolution transmission electron microscope. So you guys don't have a high-resolution transmission electron microscope. The one we use is about $1.5 million, and it's actually not good enough. And so, but these atomic force microscopes work by actually having it's like a record player needle with a really sharp tip that can bounce along the surface of DNA or on the surface of a semiconductor or anything you actually stick under there. And it's interacting with the surface. Say you have this DNA underneath it. These are chromosomes. And there's a laser that goes and hits the surface and bounces off to a detector. And so what it allows you to do is look at things at really small scale. Basically, that they can be wet, they can be dry, but you don't have to do special preparation for them. And so I'm just going to show you these kind of images in case you've never looked at atomic force microscopy images. These are 2 students of mine that they've both graduated now. Yu Wang is a professor at UCLA, Chung Yi is at Johnson & Johnson. Their idea was to engineer a virus to stick to a gold electrode, cross the gold electrode, and then have a gene to grow gold or silver or some kind of electronic material in between to make a little nanowire, basically nanoelectrode. And so they did that very successfully. They gave it the gene, it grew it. I'll show you this. This is atomic force microscopy image here, these colored images. And it had pretty good electrical properties. But again, this is not the change the world technology. This is one virus crossing an electrode. We wanted to build devices. And I'll spend the rest of the time, I have 5 minutes. This is going to be rapid. The rest of the time talking about batteries. So we've been engineering viruses to make lithium-ion batteries. You guys are all probably using lithium-ion batteries right now in your cell phones and your laptops. You probably know about exploding virus. I'm sorry, not virus. Our virus batteries don't explode. Sorry. About exploding batteries. But there's all kinds of things that are important: storage capacity, energy density, power density, rate capability involved in batteries. So in batteries, you have 2 different electrodes, a negative electrode and a positive electrode. We'll talk a little bit more about it in a minute. But about 75% of the mass of the battery that you have in your cell phone right now is wasted space and wasted mass. One of the things that's important in a battery is something called energy density, how much energy you can store in a certain amount of space. And so getting rid of that wasted space is important. So we started think about biology. Think about how DNA is packaged in the nucleus of your cells, how efficiently it's packed in there, tightly packed in there. Can we use biology to start thinking about how to redesign batteries? Okay, so here's a negative electrode. The negative electrode that you have right now in your cell phones is graphite. The positive electrode you have right now is something called lithium cobalt oxide. It's one of those materials that does explode at times, at bad times. And then you have these lithium ions. So this is a way of going from chemical energy to electrical energy. You have these ions that actually go back and forth between these structures, and that's how these batteries are working. Lithium ions, positive electrode, going back in and basically storing and retrieving energy. So my students decided, well, let's take M13, let's take this virus and get it to grow an electrode material. We're going to use cobalt oxide, a metal oxide electrode. Let's use self-assembly, have a virus self-assemble itself, and then let's use additional evolution to see if it can become better and better and better. And that's one thing that I really like about biology, is that if you can get it to do something at all, even if you get a crummy electrode material or a crummy battery material at all, you have the power of evolution on your side. So even if it's bad, it can get better and better and better if you can train it and give it that opportunity. And so that's been really, really fun for us. So this is my students' first battery. They made this in a shaker in the lab. Just basically, it had to be 37 degrees to grow the virus. And then they actually were able to pull out little single virus electrodes that are going to be used for a battery electrode here. And in case you've never built a battery before, you have to have something that is a way of getting the electrons out. You have things that are called current collectors in and out. So this is copper. We actually got a virus to grow cobalt oxide electrode material at room temperature. And then we put electrolyte in between, and we put lithium on top. So I'm not expecting you to be battery experts, but I'll show you some real battery data anyway. This is a graph. This axis over here is specific capacity. This is related to the amount of energy that you can store from your battery electrode. And this is cycle. So you know that your rechargeable batteries have to charge, discharge, charge, discharge. You want that to happen fast, and you want it to go all the way up in terms of what its maximum capacity is. And you'd like it to happen for at least hundreds of times, right? You're going to be mad if you charge and discharge your iPhone 5 times and then you need a new one. So this is actually data. This is your commercially available batteries right now in terms of what its energy, what its specific capacity is. It's right around here, around 300. This is the theory of what we thought our materials would be able to reach, and this is actual real data. So we reach theory, and it starts to fade as you charge and discharge. So we're really excited, less excited, less excited. But at least we're better than commercially available batteries. And we actually got about 2 times better than commercially available batteries our first try out, or at least the first try my students told me about. And so then my students decided, well, let's go in and let's engineer this virus to be better. Okay? It worked pretty well, but how good can you get it to be? And again, this is a lot of battery detailed information, and it's probably even beyond the scope of first-year chemistry. But again, thinking about how you have those 2 electrodes and how those lithium atoms are going back and forth between those 2 electrodes, that's ionic conductivity. These are going back and forth by using a plus charge going between these. But in order to be a good battery electrode, you need to be a good ionic conductor and a good electrical conductor. Okay? And so what my students decided to do is go and give a virus 2 genes, one to be a good ionic conductor and one to be a good electrical conductor. And they re-engineered it. And then what they did, these are actually transmission electron microscope images. This is a virus in high resolution, this is 50 nanometer length scale, where it has 2 genes, one to grow gold, one to grow cobalt oxide. We give it gold, and it starts growing gold. But you see all the spaces in between. It's not a perfect wire. All those spaces in between is where it has the sequences to grow the good ionic conductor. Now we add the cobalt in solution, and it fills in all the spaces, and now you have a new material. It's a cobalt oxide gold. It's a good ionic conductor and a good electrical conductor. And we go and we test this material as a battery electrode material. Again, this is our first try. So here's commercial available down here. Here's our first try. Here's our second try. And it actually lasts much, much longer. It's stable much, much longer. I probably have like a minute left here. So we wanted to be able to show how these could self-assemble. And so I worked with Professor Paula Hammond at MIT to make something called weak polymer electrolytes. These are a solution of something that's positive and a solution that's something that's negative. That's basically an organic molecule. And what she does is she actually takes a glass slide, sticks it in positive, sticks it in negative, sticks it in positive, sticks it in negative. And what it does is it makes this nice layer, film, of positive and negative on top of each other. Now that can actually be used to hold the electrolyte in your battery. So what kind of image is this? Atomic force microscopy image. We engineered our viruses to like her electrode polymer, and now they actually all stack on top of each other. Now you give it cobalt, and it zips up and grows the structure here. That's a cobalt oxide battery structure. And so here's the process. Take a slide, dip in polymer, dip in virus, dip in the battery material, and you pull out this battery that's transparent, and it's about almost 3 times better than commercially available batteries. And my students stopped giving it to me because it is transparent, and I drop it, and it's actually really hard to find. It's actually like saran wrap. It has some pretty good mechanical properties to it. So it's a self-assembled, room temperature grown, virus-based battery. Here's another picture of it here. Now, because I'm out of time, I should say we spent a lot of time making cathode materials, and just in the last couple of weeks, we've been able to engineer 3 genes in a virus now to make really extraordinary batteries that can go for hundreds and hundreds of cycles at almost full capacity, using a material called amorphous iron phosphate that people started looking at years ago and have discounted it because it wasn't good enough. But through genetic engineering, 3 genes, we've been able to get it to something that's actually that's as good as some of the best batteries that people are looking at now for like the Chevy Volt and batteries that could be used for plug-in hybrids. So the same technology can be applied to solar cells, has been applied to solar cells, and all other kinds of things. I'm out of time. I'd love to take questions at the end, and I'd like to thank you for your attention.
All right, while my slides are being set up, it's actually interesting to hear Angela's students stop giving this clear thing because she breaks it or lose it. I think there's something about that as I walk into the lab and none of the demos work, and students swear that they were working until the moment I walked in. And when I was a grad student or undergrad, I used to always say, like, is there something about those, important people, and then all the demos stopped working, so we somehow achieved that goal. So that's a sign when things don't work around you, you might be pretty important. So you should be aware. So this MacArthur thing, I was going to even start with telling you about it. So, maybe you're thinking there's something you're going to achieve in your lifetime that's going to make you famous. And then I've also wanted to be famous in some way. MacArthur thing, the genius thing, okay, maybe fame comes with it, maybe. So one of the things that happened, I don't know if it has happened to you, but I was sitting in the airport recently to go to give a talk in Cleveland, and I was with my son and dressed up in the crappy clothes, and then two guys were staring at me, and I thought, oh boy, I have some slobby things on me, I should just hide somewhere. And then one of the guys come over and says, excuse me, are you the certified genius? I said, I guess so. And then he just yells across to his buddy and says, hey, she's the one, she's the genius one. So then they come over and start talking, and then lots of people start coming and talking, and then we had to get on board. And then once we were on board, the seatbelt sign went ting and came off. People actually lined up in an aisle to ask me questions. And I thought, wow, I finally achieved this status of this famous thing. This is how it must be like to be a rock star. But the questions were kind of funny. The questions were mostly about, oh, I have this big concern. I think my son is a genius. And I really would like to know what he should be doing. He's only 4 years old. But should he be taking some math classes? What should he be doing? So it's really interesting to know that, a lot of people, this genius thing is, overrated. But it's in all of us. And it's in, every definition, and I think it's really fun that sometimes you just get exposed to those things. Do I have to keep cracking jokes?
Yes.
All right. What else do I have in my sleeves? Well, I can actually start by talking about my days at City College. I went to a local school called Dunn School up in the valley over, and I decided that I really wanted to play college-level tennis. And this was an excellent place to do it, and that's really first why I arrived to Santa Barbara City College. As I started pursuing my tennis, I have come to realize that my body might not be made for tennis. I was always kind of half broken, my knees and my back, and I was very famous in being in a physical therapy office. And to the point that I really I thought maybe I should pursue sports medicine. But at the same time, I thought, okay, maybe there's something else I have to pursue besides tennis in my life. And I thought, wow, this place, City College, they offer amazing classes. I really should take more of those classes and see what I can do. So that's really where I started. I thought, well, in high school, I really liked things like, oh, great, look at that. That's my title. So work hard, play hard. I think that's the way to go. And I also sort of listed my affiliations because this is sort of part of, my life was at City College. I could not decide what I wanted to do. And I thought that if I decide on one thing, then my life would be set. If I majored in math, then I'm going to be a mathematician. And I was so afraid that I just went everywhere, and I think I even have a slide on that. Oh, here we go. See, me on the Santa Barbara City College tennis court playing tennis. This was actually from the newspaper the Santa Barbara City College had. I just pulled out and scanned it. But if you look carefully, I'm wrapped around in tape everywhere. Yeah, and I have even picture of, another one I should really scan is a picture of me being treated on the physical therapy table, and then like 2 people are like treating me and wrapping me, and I'm doing my homework. So that's another one. But anyway, so that's where I started. And then I initially thought, I want to do math. And I thought, well, actually math here is amazing, right? Math here, of course, Mike was an amazing teacher, but beyond that, this is like better than UCSB. I took classes at UCSB, and then those classes were huge, and here you got personal attention, and I learned so much. But I thought, like, do I really want to be a mathematician all my life? And I thought, no, I want to do applied math. I want to apply math to do something like calculate the traffic flow and figure out how much to tilt the highway. I thought that'd be really cool, but then I thought, I really like physical things. I want to do physics. Then I thought, no, I want to do something more practical like nutrition. Then I thought, maybe I want to do pre-med. I got as close to about here to there for a cadaver in the Santa Barbara City College before I decided that I'm not going to do pre-med. Then I finally found this thing called engineering. And that kind of hit me, and I thought, wow, engineering is kind of fun. It's like takes all those things that I just wanted to do, like math and physics and even some science, and then I get to actually do something applied. So once I settled on engineering, I went to talk to a bunch of counselors here and said, engineering seems to come in different flavors, like mechanical and electrical, and which one do I do? And I sort of started browsing all those things, and then they said, well, mechanical engineering, you get to sort of play with mechanical stuff. I said, all right. And electrical stuff, you get to actually put, wires and then conduct current, and, and computers, you just sit on a terminal and program a lot. And I thought, wow, that's kind of a weird description, but I'm not sure which one to go into. So I pretty much tossed a coin, and then I applied to all different colleges with different majors, and ended up majoring in electrical engineering and computer science at Berkeley. Turns out, before that I should tell you about this one. So, Santa Barbara City College has this thing called Minority Engineering Club. They're a bunch of non-minority people, so even if you're not minority, you should join it. It was really, really cool. So you go to this meeting, and then counselors are there, and the students are there. You have great discussions about how to become engineers, and there are great mentors who tell you what to do. And then we got to go to job fairs and got to party, and then that was really fun. And this job fair I went to in LA with a bunch of people from this, I got a job at Apple Computer. And that was really, really good. And then that was my first experience that I really got. And then because of all those experiences at Santa Barbara City College, and Apple Computer was a stepping stone. Then I went to UC Berkeley, and then I majored in electrical engineering and computer science. And that was just the right thing for me, because I finally realized that what I wanted to do in my life was to connect tennis, something that I thought I wanted to do all my life, to this engineering part. And this is what I really wanted to build, a tennis buddy for myself. So this is something that I've drawn up a long time ago and thought, well, tennis, if you play any individual sports, you know that when you play, your opponent better be about the same level as you, or else if they're really much not as good as you, then it's really boring, and if they're much better, they're probably bored. So I thought it would be, if I had this tennis player and I could turn the knob depending on which day it is, it would be really awesome. Some days I'm tired, I just want to beat somebody really badly, and maybe I turn all those things down. And some days I want to be challenged, and then maybe I can turn all those things up. So I